Hi everyone, I'm Sung Jun Hong from Korea University. Thank you for coming to my talk. This is co-worked with Junhee Lee, Jung-soo Lee, and Hak Ju. This talk is about an automatic repair of memory errors found by static bug finders. In this work, we combined our tool SAVER to Infer, a state-of-the-art static analyzer deployed within Facebook, and we demonstrate that SAVER was able to fix a large portion of memory errors found by Infer. The motivation of our work is that memory errors are highly prevalent in C, but fixing them still requires a manual process. Now I'm going to describe our goal in more detail with a motivating example. This code snippet is from a program Snort, which is an open source network intrusion detection system written in C with about 300,000 lines of code. Let me first describe this program code. First, at line 8, the loop iterates over the list Lx. At each loop iteration, a data object is allocated at line 9. At line 10, the data stored in the current node is copied to allocated data object. After the copying the data, the object is appended to list Ly through a function append data. The function returns 0 if the data is successfully stored to list Ly. Otherwise, it returns -1, indicating that it fails to store the data. Infer alerts a potential memory leak warning, which is a true alarm. A memory leak occurs when the append data function fails to append the data object to the list. Once it fails, the object leaks at the next iteration. This is because it loses its only reference dptr as a new object is allocated to the pointer. Infer generates an error report for this leak like this. Given this error report, SAVER generates a correct patch by inserting a conditional deallocation after line 11. SAVER guarantees the safety of this patch, verifying that the patch deallocates leak object only. All the previous works failed to repair this particular error. They can be classified into two groups, one that guarantees the safety of the patch and the other that does not. Leakfix and Memfix generate a patch only when its safety is proved by underlying analysis. On the other hand, FootPatch does not consider whether the patch is safe or not. Those safe techniques cannot fix this error. This is because they cannot insert conditional freeze, and additionally, they are either unscalable or imprecise to analyze this code. By contrast, FootPatch generates a fix by inserting freeze statement at line 12. This fixes memory leak, but is unsafe since it introduces a new use after free. The use after free occurs because the patch also deallocates successfully appended object, which can be used after the loop ends. Our goal is to develop a new technique to overcome these previous shortcomings. From now on, I will explain the key idea of how SAVER generates a patch with a simple example. The code on the left has a memory leak error. The object O1 allocated at line 1 leaks if the controller takes the false branch. To fix the memory leak, SAVER first runs a static heap analysis to convert the input program into the object flow graph. This graph statically describes the life cycle of each heap object. A vertex of the graph represents a heap object at a certain program point and a path condition. For example, a vertex here denotes the object O1 is available at line 6 when the true branch is taken during program execution. An edge represents the control flow of a program labeled with events that could occur for the destination object. For example, edge indicates that the object is freed when it flows from line 6 to 7 under the condition C. Here, an epsilon label indicates that no event occurred. This way, the object flow graph summarizes the behavior of a heap object. After drawing the OFG, SAVER tries to fix the error by relabeling the graph. Note that memory leak is captured by this red path. Concatenating labels over the path produces the string of events here. This string indicates that the object is allocated and used along the path, but it becomes unreachable without being freed. To get rid of this error pattern, SAVER can use the full labeling strategies on the left. For example, SAVER can pull the user label backward to fix a use after free like this. In this code, to correct the memory leak pattern, SAVER replaces the empty label epsilon of this edge with a free label. Finally, SAVER converts the labeling into a patch. We can infer from the edge itself that the patch must be applied after line 6 and the path condition not C is required. We can also infer that the pointer expression to which free must be applied is P from the points to information associated to each vertex. The core idea of SAVER is not applicable to huge programs because OFG describes inter-procedure flow and fast-sensitive heap information, so computing it for the entire program is very costly. So we came up with two heuristics to improve the scalability. First, we devised the slicing technique, which only leaves program parts relevant to given error report. SAVER prepares in advance a flow-insensitive globe points to information and uses the information to fit in the missing information from the sliced part. Second, SAVER uses a path merging heuristics, which leads to selectively distinguishing the path. This is done by using the path merging heuristics. For example, separating two branches of the first conditioner does not help discriminating erroneous object from the normal one. So SAVER merges this path into one. From now on, I'm going to show the evaluation of our technique. We evaluated SAVER by comparing the fixed ratio for the Infer detected leaks from VRC project. We collected 3 projects from FootPatch benchmark set and 7 from GitHub. Their lines of code range from 2,000 to 320,000. For those benchmarks, Infer produces 96 true alarms and 66 false alarms. SAVER generated patches for 74% of true alarms, all of which were correct except for one case. That one case was incorrect but a safe fix. FootPatch generated patches for 27% of the alarms where the caller was unsafe or incorrect. FootPatch also generated patches for 40% of false alarms, which was all unsafe except for one. The interesting point is that SAVER systematically rejects any patches for false alarms. We also evaluated SAVER for double free and use after free. We could not find an effective static bug finders capable of detecting these errors, so we manually constructed our benchmarks from 34 fixed commits in GitHub. The results show that SAVER was able to fix 44% of total errors. Most of the unfixed errors are related to complex data structures or deallocation functions. In those cases, SAVER could not properly generate correct patches. Okay, let me conclude my talk. So far, debugging memory errors was a tedious and difficult task at the same time. With SAVER, this burden can be greatly reduced on the part of the developer. This is the end of my talk. Thank you for listening.